Now that we have all the pieces ready, let's assemble those into a working program. Listing 5.29 is able to compute a hard-coded mathematical expression. Here is its output. This calculation is made without the source code that you may be used to. You will need to make do with interpreting hexadecimal numbers. To help, Figure 5.4 illustrates what happens within the CPU during CPU.run. The arrows reflect the state of the CPU.position_in_memory variable as it makes its way through the program. Listing 5.29 shows our completed emulator for CPU RIA/3, the caller. You'll find the source code for this listing in this file. As you delve into systems documentation, you will find that real-life functions are more complicated than simply jumping to a predefined memory location. Operating systems and CPU architectures differ in calling conventions and in their capabilities. Sometimes operands will need to be added to the stack. Sometimes they'll need to be inserted into defined registers. Still, while the specific mechanics can differ, the process is roughly similar to what you have just encountered. Congratulations on making it this far. Section 5.7.5, CPU 4, adding the rest. With a few extra opcodes, it's possible to implement multiplication and many more functions within your inchoate CPU. Check the source code that comes along with the book. Specifically, the ch5/ch5-CPU4 directory at github.com/rust-in-action/code for a fuller implementation of the Chip 8 specification. The last step in learning about CPUs and data is to understand how control flow works. Within Chip 8, control flow works by comparing values in registers, then modifying position_in_memory depending on the outcome. There are no while or for loops within a CPU. Creating these in programming language is the art of the compiler writer. Summary. The same bit pattern can represent multiple values, depending on its data type. Integer types within Rust's standard library have a fixed width. Attempting to increment past an integer's maximum value is an error called integer overflow. Decrementing past its lowest value is called integer underflow. Compiling programs with optimization enabled, for example via cargo build -- release, can expose your programs to integer overflow and underflow as runtime checks are disabled. Endianness refers to the layout of bytes in multi-byte types. Each CPU manufacturer decides the endianness of its chips. A program compiled for a little endian CPU malfunctions if one attempts to run it on a system with a big endian CPU. Decimal numbers are primarily represented by floating point number types. The standard that Rust follows for its F32 and F64 types is IEEE 754. These types are also known as single precision and double precision floating point. Within F32 and F64 types, identical bit patterns can compare as unequal, e.g., F32 NAND does not equal F32 NAND, and differing bit patterns can compare as equal, e.g., -0 == 0. Accordingly, F32 and F64 only satisfy a partial equivalence relation. Programmers should be mindful of this when comparing floating point values for equality. Bitwise operations are useful for manipulating the internals of data structures. However, doing so can often be highly unsafe. Fixed point number formats are also available. These represent numbers by encoding a value as the nominator and using an implicit denominator. Implement std convert from when you want to support type conversions. But in cases where the conversion may fail, the std convert try from trait is the preferred option. A CPU opcode is a number that represents an instruction rather than data. Memory addresses are also just numbers. Function calls are just sequences of numbers. Chapter 6. Memory. This chapter covers what pointers are and why some are smart, what the terms stack and heap mean, how a program views its memory. This chapter provides you with some tacit knowledge held by systems programmers about how a computer's memory operates. It aims to be the most accessible guide to pointers and memory management available. You will learn how applications interact with an operating system, or OS. Programmers who understand these dynamics can use that knowledge to maximize their program's performance while minimizing their memory footprint. Memory is a shared resource, and the OS is an arbiter. To make its life easier, the OS lies to your program about how much memory is available and where it's located. Revealing the truth behind those lies requires us to work through some prior knowledge. This is the work of the first two sections of the chapter. Each of the 4 sections in this chapter builds on the previous one. None of these sections assume that you've encountered the topic before. There is a fairly large body of theory to cover, but all of it is explained by examples. In this chapter, you'll create your first graphical application. The chapter introduces little new Rust syntax as the material is quite dense. You'll learn how to construct pointers, how to interact with an OS via its native API, and how to interact with other programs through Rust's foreign function interface. Section 6.1. Pointers. Pointers are how computers refer to data that isn't immediately accessible. This topic tends to have an aura of mystique to it. That is not necessary. If you've ever read a book's table of contents, then you've used a pointer. Pointers are just numbers that refer to somewhere else. If you've never encountered systems programming before, there's a lot of terminology to grapple with that describes unfamiliar concepts. Thankfully, though, what's sitting underneath the abstraction is not too difficult to understand. The first thing to grasp is the notation used in this chapter's figures. Figure 6.1 introduces 3 concepts. The arrow refers to some location in memory that is determined at runtime rather than at compile time. Each box represents a block of memory, and each block refers to a U-size width. Other figures use a byte or perhaps even a bit as the chunk of memory these refer to. The rounded box underneath the value label represents 3 contiguous blocks of memory. For newcomers, pointers are scary and at the same time awe-inspiring. Their proper use requires that you know exactly how your program is laid out in memory. Imagine reading a table of contents that says Chapter 4 starts on page 97, but it actually starts on page 107. That would be frustrating, but at least you could cope with the mistake. A computer doesn't experience frustration. It also lacks any intuition that it has pointed to the wrong place. It just keeps working, correctly or incorrectly, as if it had been given the correct location. The fear of pointers is that you will introduce some impossible to debug error. We can think of data stored within the program's memory as being scattered around somewhere within physical RAM. To make use of that RAM, there needs to be some sort of retrieval system in place. An address space is that retrieval system. Pointers are encoded as memory addresses, which are represented as integers of type usize. An address points to somewhere within the address space. For the moment, think of the address space as all of your RAM laid out end-to-end in a single line. Why are memory addresses encoded as a usize? Surely there is no 64-bit computer with 2 to the 64 bytes of RAM. The range of this address space is a facade provided by the OS and the CPU. Programs only know an orderly series of bytes, irrespective of the amount of RAM that is actually available in the system. We discuss how this works later in the virtual memory section of this chapter. Note: Another interesting example is the option of T type. Rust uses null pointer optimization to ensure that an option of T occupies 0 bytes in the compiled binary. The none variant is represented by a null pointer, a pointer to invalid memory, allowing the sum of T variant to have no additional indirection. What are the differences between references, pointers, and memory addresses? References, pointers, and memory addresses are confusingly similar. A memory address, often shortened to address, is a number that happens to refer to a single byte in memory. Memory addresses are abstractions provided by assembly languages. A pointer, sometimes expanded to raw pointer, is a memory address that points to a value of some type. Pointers are abstractions provided by higher-level languages. A reference is a pointer, or in the case of dynamically sized types, a pointer and an integer with extra guarantees. References are abstractions provided by Rust. Compilers are able to determine spans of valid bytes for many types. For example, when a compiler creates a pointer to an I32, it can verify there are 4 bytes that encode an integer. This is more useful than simply having a memory address, which may or may not point to any valid data type. Unfortunately, the programmer bears the responsibility for ensuring the validity for types with no known size at compile time. Rust references offer substantial benefits over pointers. References always refer to valid data. Rust references can only be used when it's legal to access their referent. I'm sure you're familiar with this core tenet of Rust by now. References are correctly aligned to multiples of usize. For technical reasons, CPUs become quite temperamental when asked to fetch unaligned memory. They operate much more slowly. To mitigate this problem, Rust types actually include padding bytes so that creating references to these does not slow down your program. References are able to provide these guarantees for dynamically sized types. For types with no fixed width in memory, Rust ensures that a length is kept alongside the internal pointer. That way, Rust can ensure that the program never overruns the type's space in memory. Note: the distinguishing characteristic between memory addresses and the 2 higher abstractions is that the later 2 have information about the type of their referent. Section 6.2. Exploring Rust's reference and pointer types. This section teaches you how to work with several of Rust's pointer types. Rust in Action tries to stick to the following guidelines when discussing these types. References. Signal that the Rust compiler will provide its safety guarantees. Pointers. Refer to something more primitive. This also includes the implication that we are responsible for maintaining safety. There is an implied connotation of being unsafe. Raw pointers. Used for types where it's important to make their unsafe nature explicit. Throughout this section, we'll expand on a common code fragment introduced by Listing 6.1. Its source code is available in ch6/ch6-pointer-intro.rs. In the listing, 2 global variables, capital B and capital C, are pointed to by references. Those references hold the addresses of capital B and capital C respectively. A view of what's happening follows the code in figures 6.2 and 6.3. Listing 6.1 has 3 variables within its main function. A is rather trivial. It's just an integer. The other 2 are more interesting. B and C are references. These refer to 2 opaque arrays of data, capital B and capital C. For the moment, consider Rust references as equivalent to pointers. The output from one execution on a 64-bit machine is as follows. Figure 6.3 provides a view of the same example in an imaginary address space of 49 bytes. It has a pointer width of 2 bytes, or 16 bits. You'll notice that the variables B and C look different in memory, despite being the same type as in listing 6.1. That's due to that because the listing is lying to you. The greedy details and a code example that more closely represents the diagram in Figure 6.3 are coming shortly. As evidenced in Figure 6.2, there's only one problem with portraying pointers as arrows to disconnected arrays. These tend to de-emphasize that the address space is contiguous and shared between all variables. For a more thorough examination of what happens under the hood, listing 6.2 produces much more output. It uses more sophisticated types instead of references to demonstrate how these differ internally and to correlate more accurately what is presented in Figure 6.3. The following shows the output from listing 6.2. For readers who are interested in decoding the text within capital B and capital C, listing 6.3 is a short program that almost creates a memory address layout that resembles Figure 6.3 more closely. It contains a number of new Rust features and some relatively arcane syntax, both of which haven't been introduced yet. These will be explained shortly. In listing 6.3, COW stands for copy on write. This smart pointer type is handy when an external source provides a buffer. Avoiding copies increases runtime performance. stdffi is the foreign function interface module from Rust standard library. Use std os raw c_char is not strictly needed, but it does make the code intent clear. C does not define the width of its char type in its standard, although it's 1 byte wide in practice. Retrieving the type alias c_char from the std os raw module allows for differences. To thoroughly understand the code in listing 6.3, there's quite a bit of ground to cover. First, we'll need to work through what raw pointers are and then discuss a number of feature-rich alternatives that have been built around them. Section 6.2.1 Raw Pointers in Rust. A raw pointer is a memory address without Rust standard guarantees. These are inherently unsafe. For example, unlike references, $T, raw pointers can be null. If you'll forgive the syntax, raw pointers are denoted as *const T and *mute T for immutable and mutable raw pointers, respectively. Even though each is a single type, these contain 3 tokens, const or mute. Their type, T, a raw pointer to a string, looks like *const string. A raw pointer to an I32 looks like *mute I32. But before we put pointers into practice, here are 2 other things that are useful to know. The difference between a *mute T and a *const T is minimal. These can be freely cast between one another and tend to be used interchangeably, acting as in-source documentation. Rust references, *mute T and &T, compile down to raw pointers. That means it's possible to access the performance of raw pointers without needing to venture into unsafe blocks. The next listing provides a small example that coerces a reference to a value, $T, creating a raw pointer from an I64 value. It then prints the value and its address in memory via the :p surrounded by curly braces syntax. The terms pointer and memory address are sometimes used interchangeably. These are integers that represent a location in virtual memory. From the compiler's point of view, though, there is one important difference. Rust pointer types, *const T and *mute T, always point to the starting byte of T, and these also know the width of type T in bytes. A memory address might refer to anywhere in memory. An I64 is 8 bytes wide, 64 bits divided by 8 bits per byte. Therefore, if an I64 is stored at address 0 × 7FFFD, Then each of the bytes between 0 times 7FFFD and 0 times 8004 must be fetched from RAM to recreate the integer's value. The process of fetching data from RAM from a pointer is known as dereferencing a pointer. The following listing identifies a value's address by casting a reference to it as a raw pointer via std-mem transmute. Under the hood, references &t and &mute-t are implemented as raw pointers. These come with extra guarantees and should always be preferred. Warning: accessing the value of a raw pointer is always unsafe. Handle with care. Using raw pointers in Rust code is like working with pyrotechnics. Usually the results are fantastic. Sometimes they're painful. And occasionally they're tragic. Raw pointers are often handled in Rust code by the OS or a third-party library. To demonstrate their volatility, let's work through a quick example with Rust's raw pointers. Creating a pointer of arbitrary types from any integer is perfectly legal. Dereferencing that pointer must occur within an unsafe block, as the following snippet shows. An unsafe block implies that the programmer takes full responsibility for any consequences. To reiterate, raw pointers are not safe. These have a number of properties that mean their use is strongly discouraged within day-to-day Rust code. Raw pointers do not own their values. The Rust compiler does not check that the referent data is still valid when these are accessed. Multiple raw pointers to the same data are allowed. Every raw pointer can have write, read-write access to data. This means there is no time when Rust can guarantee that shared data is valid. Notwithstanding those warnings, there are a small number of valid reasons to make use of raw pointers. It's unavoidable. Perhaps some OS call or third-party code requires a raw pointer. Raw pointers are common within C code that provides an external interface. Shared access to something is essential, and runtime performance is paramount. Perhaps multiple components within your application require equal access to some expensive-to-compute variable. If you're willing to take on the risk of one of those components poisoning every other component with some silly mistake, then raw pointers are an option of last resort. Section 2.2, Rust Pointer Ecosystem. Given that raw pointers are unsafe, what is the safer alternative? The alternative is to use smart pointers. In the Rust community, a smart pointer is a pointer type that has some kind of superpower, over and above the ability to dereference a memory address. You'll probably encounter the term wrapper type as well. Rust smart pointer types tend to wrap raw pointers and bestow them with added semantics. A narrower definition of smart pointer is common in the C communities. There, authors, generally, imply that the term smart pointer means the C equivalents of Rust's core PTR unique, core PTR shared, and std-rc weak types. We will introduce these types shortly. Note: the term fat pointer refers to memory layout. Thin pointers, such as raw pointers, are a single U size width. Fat pointers are usually 2 U size wide, and occasionally more. Rust has an extensive set of pointer and pointer-like types in its standard library. Each has its own role, strengths, and weaknesses. Given their unique properties, rather than writing these out as a list, let's model these characters in a card-based role-playing game, as shown in Figure 6.4. Each of the pointer types introduced here are used extensively throughout the book. As such, we'll give these fuller treatment when that's needed. For now, the 2 novel attributes that appear within the Powers section of some of these cards are interior mutability and shared ownership. These 2 terms warrant some discussion. With interior mutability, you may want to provide an argument to a method that takes immutable values. Yet, you need to retain mutability. If you're willing to pay the runtime performance cost, it's possible to fake immutability. If the method requires an owned value, wrap the argument in cell of t. References can also be wrapped in ref cell of t. It is common when using the reference counted types rc of t and arc of t, which only accept immutable arguments, to also wrap those in cell of t or ref cell of t. The resulting type might look like rc of ref cell of t. This means that you pay the runtime cost twice, but with significantly more flexibility. With shared ownership, some objects, such as network connection or perhaps access to some OS service, are difficult to mold into the pattern of having a single place with read-write access at any given time. Code might be simplified if two parts of the program can share access to that single resource. Rust also allows you to do this, but again, at the expense of a runtime cost. Section 6.2.3. Smart Pointer Building Blocks. You might find yourself in a situation where you want to build your own smart pointer type with its own semantics. Perhaps a new research paper has been released and you want to incorporate its results into your own work. Perhaps you're conducting the research. Regardless, it might be useful to know that Rust pointer types are extensible. These are designed with extension in mind. All of the programmer-facing pointer types, like box of t, are built from more primitive types that live deeper within Rust, often in its core or alloc modules. Additionally, the C++ smart pointer types have Rust counterparts. Here are some useful starting points for you when building your own smart pointer types. Core PTR unique is the basis for types such as string, comma, box of t, and the pointer field vec of t. Core PTR shared is the basis for rc of t and arc of t, and it can handle situations where shared access is desired. In addition, the following tools can be handy in certain situations. Deeply interlinked data structures can benefit from std_rc weak and std_arc weak for single and multi-threaded programs respectively. These allow access to data within RC or ARC without incrementing its reference count. This can prevent never-ending cycles of pointers. The alloc raw_vec raw vec type underlies vec of t and vec deq of t, an expandable double-ended queue that hasn't appeared in the book so far. It understands how to allocate and deallocate memory in a smart way for any given type. The std cell unsafe cell type sits behind both cell of t and ref cell of t. If you would like to provide interior mutability to your types, its implementation is worth investigating. A full treatment of building new safe pointers touches on some of Rust's internals. These building blocks have their own building blocks. Unfortunately, explaining every detail will diverge too far from our goals for this chapter. Note: inquisitive readers should investigate the source code of the standard library's pointer types. For example, the std cell ref cell type is documented at this URL. Clicking the SRC button on that web page directs you to the type's definition. Section 6.3. Providing programs with memory for their data. This section attempts to demystify the terms the stack and the heap. These terms often appear in contexts that presuppose you already know what they mean. That isn't the case here. We'll cover the details of what they are, why they exist, and how to make use of that knowledge to make your programs leaner and faster. Some people hate wading through the details, though. For those readers, here is the salient difference between the stack and the heap. The stack is fast. The heap is slow. That difference leads to the following axiom. When in doubt, prefer the stack. To place data onto the stack, the compiler must know the type size at compile time. Translated to Rust, that means, when in doubt, use types that implement sized. Now that you've got the gist of those terms, It's time to learn when to take the slow path and how to avoid it when you want to take a faster one. Section 6.3.1. The stack. The stack is often described by analogy. Think of a stack of dinner plates waiting in the cupboard of a commercial kitchen. Cooks are taking plates off the stack to serve food, and dishwashers are placing new plates on top. The unit, the plate, of a computing stack is the stack frame, also known as the allocation record. You are probably used to thinking of this as a group of variables and other data. Like many descriptions in computing, the stack and the heap are analogies that only partially fit. Even though the stack is often compared by analogy to a stack of dinner plates waiting in the cupboard, unfortunately, that mental picture is inaccurate. Here are some differences. The stack actually contains two levels of objects, stack frames and data. The stack grants programmers access to multiple elements stored within it, rather than the top item only. The stack can include elements of arbitrary size, where the implication of the dinner plate analogy is that all elements must be of the same size. So why is the stack called the stack? Because of the usage pattern. Entries on the stack are made in a last in, first out, or LIFO manner. The entries in the stack are called stack frames. Stack frames are created as function calls are made. As a program progresses, a cursor within the CPU updates to reflect the current address of the current stack frame. The cursor is known as the stack pointer. As functions are called within functions, the stack pointer decreases in value as the stack grows. When a function returns, the stack pointer increases. Stack frames contain a function's state during the call. When a function is called within a function, the older function's values are effectively frozen in time. Stack frames are also known as activation frames and, less commonly, allocation records. Footnote 1. To be precise, the activation frame is called a stack frame when allocated on the stack. Unlike dinner plates, every stack frame is a different size. The stack frame contains space for its function's arguments, a pointer to the original call site, and local variables, except the data which is allocated on the heap. Note: if you are unfamiliar with what the term call site means, see the CPU emulation section in Chapter 5. To understand what is happening more fully, let's consider a thought experiment. Imagine a diligent yet absurdly single-minded cook in a commercial kitchen. The cook takes each table's docket and places those in a queue. The cook has a fairly bad memory, so each current order is written down on a notebook. As new orders come in, the cook updates the notebook to refer to the new order. When orders are complete, the notebook page is changed to the next item in the queue. Unfortunately for customers in this restaurant, the book operates on a LIFO manner. Hopefully you will not be one of the early orders during tomorrow's lunch rush. In this analogy, the notebook plays the role of the stack pointer. The stack itself is comprised of variable length dockets, representing stack frames. Like stack frames, restaurant dockets contain some metadata. For example, the table number can act as the return address. The stack's primary role is to make space for local variables. Why is the stack fast? All of a function's variables are side by side in memory. That speeds up access, improving the ergonomics of functions that can only accept string or &str. As a library author, it can simplify downstream application code if your functions can accept both &str and string types. Unfortunately, these two types have different representations in memory. One, &str, is allocated on the stack. The other, string, allocates memory on the heap. That means that types cannot be trivially cast between one another. It's possible, however, to work around this with Rust generics. Consider the example of validating a password. For the purposes of this example, a strong password is one that is at least 6 characters long. The following shows how to validate the password by checking its length. Is_strong can only accept string. That means the following code won't work. But generic code can help. In cases where read-only access is required, use functions with the typed signature fn x of t colon as ref of str of a colon capital T, rather than fn x of a colon string. The fairly unwieldy type signature reads, as function x takes an argument password of type t, where t implements as ref of str. Implementers of as ref of str behave as a reference to str even when these are not. Here's a code snippet again for the previous listing, accepting any type t that implements as ref of str. It now has the new signature in place. When read-write access to the argument is required, normally you can make use of as ref of t's sibling trait as mut of t. Unfortunately for this example, ampersand semiquote static str cannot become mutable, and so another strategy can be deployed: implicit conversion. It's possible to ask Rust to accept only those types that can be converted to string. The following example performs that conversion within the function and applies any required business logic to that newly created string. This can circumvent the issue of ampersand str being an immutable value. This implicit conversion strategy does have significant risks, though. If a stringified version of the password variable needs to be created multiple times in the pipeline, it would be much more efficient to require an explicit conversion within the calling application. That way, the string would be created once and reused. Section 6.3.2. The heap. This section introduces the heap. The heap is an area of program memory for types that do not have known sizes at compile time. What does it mean to have no known size at compile time? In Rust, there are two meanings. Some types grow and shrink over time, as required. Obvious cases are string and vec of t. Other types are unable to tell the Rust compiler how much memory to allocate, even though these don't change size at runtime. These are known as dynamically sized types. Slices, capital T surrounded by square brackets, are the commonly cited examples. Slices have no compile time length. Internally, they are a pointer to some part of an array, but slices actually represent some number of elements within that array. Another example is a trait object, which we've not described in this book so far. Trait objects allow Rust programmers to mimic some features of dynamic languages by allowing multiple types to be wedged into the same container. What is the heap? You will gain a fuller understanding of what the heap is once you work through the next section on virtual memory. For now, let's concentrate on what it is not. Once those points are clarified, we'll then work our way back towards some form of truth. The word heap implies disorganization. A closer analogy would be a warehouse space in some medium-sized business. As deliveries arrive, as variables are created, the warehouse makes space available. As the business carries out its work, those materials are used, and the warehouse space can now be made available for new deliveries. At times, there are gaps and perhaps a bit of clutter, but overall there's a good sense of order. Another mistake is that the heap has no relationship to the data structure that is also known as a heap. That data structure is often used to create priority queues. It's an incredibly clever tool in its own right, but right now it's a complete distraction. The heap is not a data structure. It's an area of memory. Now that those two distinctions are made, let's inch towards an explanation. The critical difference from a usage point of view is that variables on the heap must be accessed via a pointer, whereas this is not required with variables accessed on the stack. Although it's a trivial example, let's consider two variables, a and b. These both represent the integers 40 and 60, respectively. In one of those cases, though, the integer happens to live on the heap, as in this example. Now, let's demonstrate that critical difference. The following code won't compile. The boxed value assigned to B is only accessible via a pointer. To access that value, we need to dereference it. The dereference operator is a unary asterisk, which prefixes the variable name. This syntax can be difficult to follow at first because the symbol is also used for multiplication. It does, however, become more natural over time. The following listing shows a complete example where creating variables on the heap implies constructing that variable via a pointer type such as box of T. To get a feel for what the heap is and what is happening within memory as a program runs, let's consider a tiny example. In this example, all we do is create some numbers on the heap and then add their values together. When run, the program in listing 6.7 produces some fairly trivial output, 2 3s. Still, it's really the internals of the program's memory that are important here, not its results. The code for the next listing is in this file. A pictorial view of the program's memory as it runs, figure 6.5, follows the code. Let's first look at the program's output. Listing 6.7 places 4 values on the heap and removes 1. It contains some new or at least less familiar syntax that might be worthwhile to cover and/or recap. Box new of T allocates T on the heap. Box is a term that can be deceptive if you don't share its intuition. Something that has been boxed lives on the heap, with a pointer to it on the stack. This is demonstrated in the first column of figure 6.5. where the number 0 times 100 at address 0 times FFF points to the value 1 at address 0 times 100. However, no actual box of bytes encloses a value, nor is the value hidden or concealed in some way. std mem drop brings the function drop into local scope. Drop deletes objects before their scope ends. Types that implement drop have a drop method, but explicitly calling it is illegal within user code. std mem drop is an escape hatch from that rule. Asterisks next to variables, asterisk A, asterisk B, asterisk C, and asterisk D are unary operators. This is the dereference operator. Dereferencing a box of T returns T. In our case, the variables A, B, C, and D are references that refer to integers. In figure 6.5, each column illustrates what happens inside memory at 6 lines of code. The stack appears as the boxes along the top, and the heap appears along the bottom. The figure omits several details, but it should help you gain an intuition about the relationship between the stack and the heap. Note: if you have experience with a debugger and want to explore what is happening, be sure to compile your code with no optimizations. Compile your code with cargo build or cargo run rather than cargo build -- release. Using the -- release flag actually ends up optimizing all the allocations and arithmetic. If you are invoking rustc manually, use the command rustc -- codegen opt - level equals 0. Section 6.3.3. What is dynamic memory allocation? At any given time, a running program has a fixed number of bytes with which it gets its work done. When the program would like more memory, it needs to ask for more from the OS. This is known as dynamic memory allocation and is shown in figure 6.6. Dynamic memory allocation is a 3-step process. 1. Request memory from the OS via a system call. In the Unix family of operating systems, this system call is alloc. In MS Windows, the call is heapalloc. 2. Make use of the allocated memory in the program. 3. release memory that isn't needed back to the OS via free for Unix systems and heap free for Windows. As it turns out, there is an intermediary between the programs and the OS, the allocator, a specialist subprogram that is embedded into your program behind the scenes. It will often perform optimizations that avoid lots of work within the OS and CPU. Let's examine the performance impact of dynamic memory allocation and strategies to reduce that impact. Before starting, let's recap why there's a performance difference between the stack and the heap. Remember that the stack and the heap are conceptual abstractions only. These do not exist as physical partitions of your computer's memory. What accounts for their different performance characteristics? Accessing data on the stack is fast because a function's local variables, which are allocated on the stack, reside next to each other in RAM. This is sometimes referred to as contiguous layout. A contiguous layout is cache-friendly. Alternatively, variables allocated on the heap are unlikely to reside next to each other. Moreover, accessing data on the heap involves dereferencing the pointer. That implies a page table lookup and a trip to main memory. Table 6.1 summarizes these differences. There is a trade-off for the stack's increased speed. Data structures on the stack must stay the same size during the lifetime of the program. Data structures allocated on the heap are more flexible. Because they are accessed via a pointer, that pointer can be changed. To quantify this impact, we need to learn how to measure the cost. To get a large number of measurements, we need a program that creates and destroys many values. Let's create a toy program. Figure 6.7 shows a background element to a video game. After running listing 6.9, you should see a window appear on your screen filled with a dark gray background. White, snow-like dots will start to float from the bottom and fade as they approach the top. If you check the console output, streams of numbers will appear. Their significance will be explained once we discuss the code. Listing 6.9 contains three major sections. A memory allocator, the reporting allocator struct, records the time that dynamic memory allocations take. Definitions of the structs, world, and particle, and how these behave over time. The main function deals with window creation and initialization. The following listing shows the dependencies for our toy program, listing 6.9. The source for the following listing is in ch6/ch6-particles/cargo.toml. The source for listing 6.9 is in ch6/ch6-particles/main.rs. Listing 6.9 is a fairly long code example, but hopefully it does not contain any code that's too alien compared to what you've already seen. Toward the end, the code example introduces Rust's closure syntax. If you look at the call to window.draw_2D, it has a second argument with vertical bars surrounding the two variable names. Vertical bar, ctx, renderer, _device, vertical bar, open brace, ... close brace. Those vertical bars provide space for the closure's arguments, and the curly braces are its body. A closure is a function that is defined in line and can access variables from its surrounding scope. These are often called anonymous or lambda functions. Closures are a common feature within idiomatic Rust code, but this book tends to avoid those where possible to keep examples approachable to programmers from an imperative or object-oriented background. Closures are explained fully in Chapter 11. In the interim, it's sufficient to say that these are a convenient shorthand for defining functions. Let's next focus on generating some evidence that allocating variables on the heap many millions of times can have a performance impact on your code. Section 6.3.4. Analyzing the impact of dynamic memory allocation. If you run listing 6.9 from a terminal window, you'll soon see two columns of numbers filling it up. These columns represent the number of bytes allocated and the duration in nanoseconds taken to fulfill the request. That output can be sent to a file for further analysis as shown in the following listing, which redirects standard error from ch-particles to a file. One interesting aspect from this short extract is that memory allocation speed is not well correlated with allocation size. When every heap allocation is plotted, this becomes even clearer as Figure 6.8 shows. To generate your own version of Figure 6.8, the following listing shows a new plot script that can be tweaked as desired. You'll find this source in the file ch6/alloc.plot. Although larger memory allocations do tend to take longer than shorter ones, it's not guaranteed. The range of durations for allocating memory of the same number is over an order of magnitude. It might take 100 nanoseconds, it might take 1,000. Does it matter? Probably not, but it might. If you have a 3 GHz CPU, then your processor is capable of performing 3 billion operations per second. If there is a 100 nanosecond delay between each of those operations, your computer can only perform 30 million operations in the same time frame. Perhaps those hundreds of microseconds really do count for your application. Some general strategies for minimizing heap allocations include using arrays of uninitiated objects. Instead of creating objects from scratch as required, create a bulk lot of those with zeroed values. When the time comes to activate one of those objects, set its values to non-zero. This can be a very dangerous strategy because you're circumventing Rust's lifetime checks. Use an allocator that is tuned for your application's access memory profile. Memory allocators are often sensitive to the sizes where these perform best. Investigate arena, and arena-typed arena. These allow objects to be created on the fly, but alloc and free are only called when the arena is created and destroyed.